Okay, so everyone, I believe everyone except one person at least, has picked up their exam now. So as you look over these, you probably have not seen your scores yet. You may have noticed that I did not put the grades in until this morning. I always do that on purpose, in case anyone's wondering. I never put the scores in until right before class. Otherwise, people who did bad see it, get discouraged, don't come to class. When if you did bad on an exam, you should definitely come to class, not skip it, right? So it is, generally speaking, a better system, though I understand also in some ways perhaps a more stressful one to some extent. So as you look at your exams, check them out and everything. Let's talk about it really quick. So these exams did not, I would broadly say, go as well as I would have hoped they went. That is, something that happens from time to time. There is always debate to be had about the reason for this. Did I perhaps make the exam too hard or too long? Debatable. Or perhaps maybe people didn't study enough. I don't know. There are always different, reasons an exam can go well or not, and it is hard to tell. I have given in various classes. One semester I gave an exam in a class, and it went so poorly that I was like, I better give these people a chance to get some points back. It was so bad. And then I gave almost an identical exam, just with some numbers changed, like a couple of years later, in exactly the same class, at exactly the same point, using exactly the same book. And the scores were so high, I was like, I feel like this is like not even a legit exam. So sometimes there is just variation, right? You are not interchangeable learning units, right? So there is variation, and it can be hard to tell what happened. That being said, this one did go, I would say, less well than I had hoped. And particularly the places it went worst were probably like parts that I had really, I guess I was surprised by in some ways. That is, I'm not trying to just be up here just blasting you or something like that. I'm not going to like tisk you and tell you how disappointed I am or something. No, nothing like that. But what I'm trying to say, I guess, is that I think a lot of people kind of got the yips, right? You got like a little spooked, I think. So I kind of expected that some people might get thrown off by some of the like, hey, like, circle, like mark all that are necessarily true, or, things like this, get thrown off by something with that. But on some of the proofs, I was very surprised by, for instance, on number 7, I don't think a single person in the entire room used the hint that I wrote under the problem. Maybe one person used the hint. But I wrote a hint, and no one used it. Why? I don't know. But hey, whatever the reason is, I guess I think it would be nice to go spend a little bit of time just talking briefly about the idea behind what you were to show in problems 6, 7, 8, and 9. Those are the ones that I would say went worst. Had the performance on those ones been slightly better, I think this would have been a relatively reasonable exam. I do have something to say about the scores. I have an offer for you guys that I think you'll like, so don't worry. Don't freak out. Don't be having like a panic attack right now and feel the room darkening around you. It's okay. I've also taken exams that have gone poorly before. I get how it is. Don't beat yourself up. But I think what happened is a lot of people on the proofs, particularly, I would say that on like 5, people generally did about as well as I would expect. That was like a kind of standard, like, show that some sets are equal. People went and showed containment in each direction. Some people also just manipulated the predicates involved in the definitions of the sets and used basic facts about propositional logic to show equality all in one step. And that went well. But then once we got to the proofs, I think a lot of people got really thrown off. So my goal with these proofs, and what I had hoped was the outcome, was that in these proofs, I tried to throw you some stuff that looked tricky, but wasn't, if you actually just like, could kind of like sort of like calmly proceed with it, right? That is like, I guess like on a lot of it, I was trying to get you to not be freaked out by the notation, right? So I'll kind of try to sketch a few of them and show you what it's saying and like what the hints are and stuff. And I think that you'll maybe agree, right? Most of them are relatively short, actually. But I think just based on what people were writing, I think a lot of people thought that they should be really hard and difficult and require like super complicated tricks just because they had hidden notation in them, right? But the goal is to hopefully, get like my thinking was that now that you've been writing proofs for a while and stuff like that, I could throw some more notation heavy stuff at you, and you could just look at it and go like, oh, okay. Actually, if I just read what it's saying, it's like not, like I'm not going to get thrown off just by there being symbols and stuff. Not that I'm saying that you all guys just all panicked or something like that, but it does seem like at least some people, I don't know, maybe you did panic a little bit, right? You saw some stuff and you're like, this looks complicated, I'm out. And my goal is to try to give you that confidence of like, it looks complicated, but it's not bad. You can do it. You've been doing this for a while, right? So let's sketch a few of them. Let's see how it's going to go. And then we'll talk about what to do. So in problem 6, we introduced the preimage. So I mentioned this one when we were talking about what would be on the exam as like the analog to when you prove stuff about the image in the homework. And this is relatively similar to what you did in the homework, but just now about preimages instead of images. So the preimage, so given a function f from x to y and z a subset of y, we define the preimage of z to be the set of all x's in x such that f of x is in z. That is, it's all the stuff that f sends from x to z. Kind of the blob picture of it is that you've got x, you've got y, f is sending stuff in x to stuff in y. You take some subset of stuff over here, let's call this z. The stuff over here, and it doesn't have to just be like one blob, it can be like a couple of blobs. This is the stuff that f sends into z. So just the collection of all the stuff that f sends into z. So it's just like all the stuff that gets sent over and lands in here. Yeah? All the x's such that f of x is in z. Okay. So the thing you were to show was that, so want to show, WTS, want to show that f inverse, or sorry, f's preimage of y set minus z was equal to x set minus the preimage of z. So the idea of this, you can go, the standard one, the easiest one that I would say that everyone's seen before, though maybe not the quickest, would have just been to do containment in both directions. So you could have been like, okay, now think about it really quick. This is one big mistake that I saw a lot of people do. Where do the things in here live? Are they in x or are they in y? In x, yeah, exactly. Since it's a preimage, it's collections of points in the domain, right? A lot of people took things in y for this part. Okay, so you want to take some x in the preimage of y set minus z, which I'll even write it, say it this way. Then f of x is in y set minus z, right? i.e. f of x is in y, and f of x is not in z. Yeah? Okay. Now, from here, all you essentially have to show, this piece right here, f of x is not in z. Does that look like a statement about preimages a little bit, right? That is, if I just write an implication here. This is not written very formally, just to kind of give you an idea. I'm not trying to give the whole thing away for reasons that we will soon discuss. That is, f of x is in y and not f of x is in z, but f of x is in z is the predicate defining the preimage of z. Yeah? That is, f of x is in y and not x is in preimage of z. You see what I'm saying? Maybe? That is, all you got to do is manipulate, effectively, this statement here. If you want to do it in the quickest way, so if you want to go this way, you take something in here, and you want to show it lives in x set minus f inverse, or f's preimage of z. You've already got not in the preimage, so in the complement of the preimage, right? That is, all you have to notice is that f of x and y, is there any x that does not land in y? If f sends x to y, all the f of x's are in y, right? Or even, I won't even write this. All of the x's are in y, and we have not in the preimage, right? So we have x is in x, and not x is in the preimage of z, which just tells you in the easiest possible way, it's in x, and it's not in this. It's in x set minus the preimage. See what I'm saying? So that would be like the kind of more laborious, like go forward, then do the same thing in the reverse direction. I think it would be personally easier, in my opinion, just to manipulate the set itself and the predicates involved. That is, if you start out just with the preimage of y set minus z, this is just equal to the set of all x's in x such that f of x is in y set minus z. Okay, but what is this? This is the x's in x such that f of x is in y and f of x is not in z, right? Feeling good about that? One of these is just a true statement, right? That is, this is just that, right? F of x is always in y. F is a function that goes from x to y. There's no way you can get something out that doesn't live in the codomain, right? That's the second blob. All of the arrows point to stuff in the blob. Okay, so simplification, true and statement is just statement, right? So it's in x such that f of x is not in z. Do you see how you end up right here? In x and not in the preimage? Yeah? Yeah, exactly. Okay, cool. So that one, I would say people had less trouble with, but I think people just got freaked out by like, here's a new notation. Oh, no. And I think, people, I would say if that one went badly, look at it and ask yourself, like, did you directly engage with what it was saying, or did you just kind of panic a little bit and just write down all the definitions, I think that one might have happened to a few people. And if it did, okay, don't worry. It's not the end of the world to have this happen. So let's look at number 7. Number 7, I intended to be quite easy with the hint, but I think since people didn't use the hint, they got a little thrown off. So here, let me show you 7 with the hint, and you're going to go, oh, okay. So we let f from x to y be a function. Show there exists a set z, a surjective function. I'm going to keep the letters the same. G from x to z, and an injective function h from z to y, such that f is equal to h composed with g. Okay, the hint, these markers are all terrible. Okay, let's see. Is this marker better? Yes, substantially so. The hint said that if you're stuck, consider the image of the domain of f. Okay, so recall really quick. And I also put this in the hint, the definition of the image. So I would say recall. For W, a subset of the domain, the image is f of W. This is just equal to the set of all. You can write it a couple different ways. I think the easiest way to write it is f of x such that x is in W. Yeah? Okay, so if you take the image of the domain, here's the picture. You've got x, you've got y, you've got f, a function between them. When you send everything through f, it's possible that you hit everything in y. It's also possible that you hit something smaller, right? You certainly can't hit anything bigger, yeah? Okay, so you get some chunk of stuff in here. And what is this? Well, this is the stuff that gets hit by some x in x, the image of the domain, right? I'll make these big x's just to be super clear. Yeah? Okay, so this is everything that f hits. Yeah? Everything in here is something that got hit by some x. Everything outside of it is the stuff that didn't get hit. So what if you take z to be the image of the domain? Can you think of a function that surjects onto it? So if we take g from x to the image of x and define g so that g of x is equal to f of x, then certainly it hits everything, right? We got rid of all the stuff that it didn't hit. Yeah? Okay. Now, all we need is a function h that takes this new set we've made, the image of the domain, to the codomain such that it's equal. What could we do? How could you send this stuff to the larger set in such a way so that they're equal? You can just make them the same, yeah? An embedding, right? The same way you can put the reals in the complex numbers just by, the function that takes the real number to itself, but treat it as a complex number, right? You see what I'm saying? That is, here's the breakdown. The breakdown looks like this. It says, hey, you've got this, right? What you're going to do is you're going to take x, and then you're going to take the image, which is this little blob, And then you have y, which is that big whole thing. And here's what you do. G is the function that just is the same as f. H is the function that just sends the things here to themselves, but as elements of y. You see what I'm saying? Yeah? So the only thing you need for this one, if you are like, I intended for it to be like, hey, look, you want something like what's blocking f from being surjective? There might be stuff you don't hit. What if you get rid of all the stuff you don't hit? Then it becomes surjective, right? And then all you have to do is take the stuff you do hit and put it back into the bigger set. What's the easiest way to do that? Just like directly put it in. Don't change it at all, right? So h is the function. G of x is just equal to f of x for all x. And h of x is just equal to x for all x. See? So there was no like crazy trick or anything like that. It was just basically kind of like a test of saying like, hey, if a function is not surjective, well, what happens? There's stuff that doesn't get hit. So you could get rid of the stuff you don't hit, and then there's a new function that agrees at every point and is surjective. Moreover, the stuff that does get hit, you can put back into the bigger set containing the stuff that also maybe doesn't get hit just by directly like putting it right in there. Exactly like that. You see what I'm saying? Okay, cool. I don't know, maybe you don't like it, but hey, there we go. That's the trick of it. The only real thing to show then is that one of them is surjective and one of them is injective, but these are hopefully very straightforward things to show, since if g of x is f of x and the codomain of g is all of the stuff that f hits, certainly everything here is by definition something that got hit by f and hence by g, right? Okay, I don't know, maybe you don't like it, but there's the trick idea of that one, I suppose, if there is a trick to it. The other ones were relatively similar in some ways of having not so much of like any sort of difficult thing to compute, but just like seeing the definitions and like parsing what they say. In many ways, that's kind of like one of the big points of this class, is not so much to like be like, hey, here's specific content. But of course, we are getting some set theory and that stuff in here, but more to like get you accustomed to writing proofs and doing the job of mathematics, which is like, hey, here's object, like give you mathematical object, proof statement about it, right? And so, giving you object and having you prove a statement about it is kind of like the bread and butter of what we are aiming to get you ready to do here. So in 8, we had X is the set A, B, C, and D, and Y was the set 1, 2, 3, 4, 5. We suppose f is a function from x to y. Barely caught that cap. And then what you were to do is prove there does not exist a function g from y to x such that f of g of y equals y for all y in y. A lot of people said, hey, well, f's not invertible, so there can't be a function. But notice, we are not claiming that f is invertible here. Only we're claiming that it does not have a right inverse. It is true that it's not invertible, but being non-invertible does not imply that you don't have a right inverse. Yeah? So here's kind of the picture to remember in your head. So say, for instance, I've got A, B, and C, and I've just got 1, 2 over here. Well, then I could take a function, pick any old one you want. Here's x, y, and y. This function is certainly not invertible, right? But I can definitely come up with a function g so that I end back where I started. I have to send 1 to something that gets mapped to 1. There's one choice. And 2 to something that gets mapped to 2. There's another choice, right? So I put 1 through G, I get A. I put A through F, I get 1. 1 got mapped to 1 when I composed them together. I put 2 through G, I get B. I put B through F, I get 2. 2 got mapped to 2 when I put them together. Yet F is still not invertible. So it is not true, as many people wrote, that the fact that F is not invertible shows that no such function exists. It is entirely possible to have no such function, or it is entirely possible to have such a function when F is not invertible. Such functions can exist for non-invertible functions. What prevents it is that F is not necessarily not surjective. That's the trick. Do you remember when we did all this stuff? We talked about left and right inverses. We did a lot of proofs of it, right? This is kind of like the focus of this one, was effectively like duplicating one of those types of arguments. So basically all this boils down to is, hey, look, F is not, like the easiest version of it is just, hey, F is not surjective. Like it can't be. And you can show that relatively straightforwardly. Since these sets are relatively small, X has only 4 elements in it, right? Y has 5. All of the stuff you get out of F cannot be all of Y, right? There must be something in Y you don't hit. So all you have to do is show that there's something in Y you don't hit. If F doesn't hit it, it doesn't matter what you put inside of it. You will never get that value out, right? And so the G is almost immaterial. It just comes down to F cannot be surjective. And then no matter what you do with the other stuff, you won't be able to hit that value that you miss, right? So that's basically the goal of it, is you want to show, hey, F is necessarily not surjective. Hence, there is some value in its codomain, that is some y, such that f of x equals y has no solution, right? If that's the case, there's nothing that G can send any y to make that, to fix that. Does that make sense? Yeah? That is, if our picture instead looks more like this right here, ABC, and instead, or maybe I have 1, 2, 3, and 4, no matter how I want to draw all these arrows, something is not going to get hit. Potentially many things won't get hit, but even in the best case scenario where F hits as much stuff as possible, there's going to be something that doesn't get hit. In this case, how I drew it, 2 doesn't get hit, right? It doesn't matter where you draw the arrows for G over here, you're still not going to get to 2 because you have to follow arrows, and there's no path to 2, right? So certainly, this is totally impossible, yeah? Even if you didn't have the argument fully formalized, anything that effectively got at look, this isn't surjective, there's going to be something you don't hit, so there can't be such a function. I gave most of the points too. So that's kind of the goal. On 9, the final one, this was one with some hey, let me throw a thing at you kind of stuff. And maybe this was where it gets a little too long. It takes a little while to ingest a new concept, so I get it. But in this one, I just said, hey, here's a quick little equivalence relation. And I wanted you to show something about some involved functions that you could make between sets of equivalence classes. So I started this one and I said, hey, every function f from a set x to a set y induces an equivalence relation on x via x1 similar to x2 if f of x1 is equal to f of x2. Yeah? Okay. Let x hat be the set of all equivalence classes of f under this relation. Show there exists a surjective function g from x hat to x if and only if f is injective. Here's the picture. Okay, so you've got your x right here. It's got a bunch of stuff, yeah? Now, when you make x hat, here's what happens. So I'm just going to put this some stuff here, like a, b. I think I even gave you the set was, I said, 1, 2, 3, and 4. Yeah? Now, when you go to x hat, what happens? Well, marker. When you go to x hat, all that happens, this is x, and when you go to x hat, all that happens is you put some of them in circles, like their equivalence classes, right? Yeah? If the second set is itself x, has 1, 2, 3, and 4 right there, and you want to hit everything, if you're grouping things up, you are ending with fewer things, at most, just as many things, right? If you have fewer things, can you have a surjective function from a set, say, with 3 elements to a set with 4 elements? No way. The only way you could have a surjective function is if these two sets had the same number of elements, right? That is, if each equivalence class contains only one element. But remember, the equivalence class of something, some x, is just the set of, I'll write it this way. Maybe I'll use z just for convenience. The equivalence class of an element z is just the set of all x's in x such that x is similar to z. Yeah? But using our definition right here, this is all x's in x such that f of x equals f of z. Yeah? So when does each of these sets only have one thing in them? When would they have 2 things in them? If there are 2 things that get mapped to the same thing by f. The only way for them to have one thing in them is if f of x equals, well, maybe even, what if I wrote a y? Well, then you see it maybe easier since we wrote y's a lot when we did injectivity. This is the set of all x's in x such that x is similar to y. That is, it's the set of all x's in x such that f of x equals f of y. When is there only one such thing? When f of x equals f of y implies x equals y, right? Injective, right? If it's not injective, more than one thing gets sent to the, there's at least one pair of elements that get sent to the same thing, which means that there are at most 3 equivalence classes, right? Since one of them has to have at least 2 things in it, yeah? So the only way you get 4 equivalence classes, that is, as many equivalence classes as there are elements, is when f is injective, yeah? So basically the whole idea of it was just saying, look, you've got some stuff. You're going to put it in little groups. The only way for you to have as many groups as you have things is if each group contains only one thing. And the thing that tells you how many things a group contains is how many things get hit by this, or how many x's get sent to the same thing, right? And so if each output has a unique input, then the function is injective and each equivalence class has only one thing in it. Yeah? Okay, so that's the idea of that one. You kind of see what I'm saying? Maybe I'm being too harsh. I don't mean to be harsh. But saying that like most of these don't have some, like you're not constructing some sort of like crazy function on the fly. You don't have to do like any real like trick with like creating things or doing like some like multi-stage like proof where you go like suppose this, let's prove the contrapositive, blah blah blah. Bunch of crazy like manipulations of propositions or something, propositional statements, predicates, etc. Most of it's just like parsing the definitions and putting them together. You get what I mean? That's kind of the goal. But all right. So enough about content on the exam. Those are the ones that I think people had the most trouble with. So here's what I think for the exam. Some humility on my part. There's a very good possibility that perhaps it was too long or maybe too hard. I don't know. It could be. So maybe I didn't give you guys like enough of a chance to show me what you know in the time allotted. So why don't we fix that by giving you another chance to show me that what you know and submit corrections for half points back? Does that sound good? Okay, if everyone did that, it would raise the class average to a nice and healthy B. And I imagine that not everyone will end up doing it. So it will put the average at a very good regular old spot. So yeah, let's do that. Let's submit corrections. And I want them to be nice, right? I don't want to have to spend like an hour on each exam, like trying to like parse through it and make, it's kind of there, some quick rush thing. I'm only gonna give you points back if you give me like a good proof, right? Give me like good solid proofs. Come ask questions if you have them. Make sure you actually get it, right? So I'll give you, you can do that for half points back and then cool. So the worse you did, the more points you get back. If you did great, then, less incentive to do it, but you probably need to do it less. So yeah.
So like, we can just...
I will also let you correct the true and false. However, I will not let you correct the true and false just by writing the opposite thing of what you wrote down. You must justify your answer, explain why it is like, the opposite of what you wrote down. Yeah. Otherwise, that would just be a waste of paper. Yeah. Yes.
You want us to do them on a separate piece of paper, I'm assuming then the exact.
It would be ideal to do it on a separate piece of paper, yes. And then also, when you submit them, please give me your exam so I can see that you have done corrections on the problems you got wrong, since I did not write down all of the problems that everyone got wrong. Yeah, so keep your exams, do your corrections, pass back the exams with your corrections, or email them to me, give them to me in person, whatever you prefer. And I'll give you half points back on what you missed, assuming you give me great answers. Cool? All right, and then, yes. That's what I was going to ask. Yeah, so for the time frame, what seems reasonable to you guys? Would like a week seem good? Some people get, I don't know.
Yeah. We don't have class next week, Wednesday, is that right?
You're right, we don't have class on Wednesdays. So maybe on Friday next week you have to give it to me. How about that?
We don't have class on.
It would be Monday.
We don't have class on Friday because it's Thanksgiving.
So it'd have to be next week, Monday, the following week, Monday.
Okay, well there's two kinds of, so this is up to you guys. And I personally don't have a huge preference between the two. Do you want it next week, Monday, so you can go into Thanksgiving break not having to worry and think about this? Or do you want the entirety of Thanksgiving break to do this at a more relaxed pace? Depends. What do you prefer? Monday? Give me a hand for Monday.
Which Monday? Which
Monday?
They're both Mondays. Okay, so the sooner one, next Monday. Does anyone prefer next Monday? Some people do. Some people, okay, who wants the Monday after break? Almost everyone wants the Monday after break. Okay, so I'll do the Monday after break. That's fine. I know there's a lot of stuff. People like to do tests right before break, which is mean. I think they shouldn't do that. Though I guess it's meaner to put a test right after break. But yeah, okay, you can have break for it. Hopefully it doesn't ruin your Thanksgiving. Don't spend, spend time with your family, right? Yeah, okay, cool. If you feel like that will ruin your Thanksgiving, I can optionally make your deadline earlier if you prefer. Come talk to me. All right. But yeah, so I see some people packing up. Oh, we are far along in the class. Well then, next time we will. That clock is substantially wrong. More wrong every day. All right, we'll call it quits then. It was an exam, a look over it day. See you next time, guys.